Let's do a two-sample t-test together. The manager of a brewery is interested in comparing the performance of two production lines, one of which has only recently been installed. For each line, she selects 10 one-hour periods at random and records the number of crates completed in each hour. Assuming that these samples came from normal populations, is there evidence that production lines complete a different amount of crates each hour at the 5% significance level? So we do have the data available to us on a tab titled Beer, and the order of subtraction that we're going to use is new minus old. All right, so the first thing we need to do is a statement about our parameters. So we need to talk about the mean of one group versus the mean of the other group. So something along the lines of, we're going to test the claim that the mean beer production on the new line differs from the mean beer production on the old line. The hypotheses, the null hypothesis will be the mean of the new minus the mean of the old is equal to 0. Or in other words, the means are about equal, or the two groups are producing about the same amount of beer on average each hour. The alternative is going to be the mean of the new, or mu of the new, minus the mean of the old is not equal to 0. And I got that not equal from the differs that we have written down in our parameter statement. The assumptions and conditions, let's start with the new line group. So random was stated in the problem, so we can check that off. Our sample size is 10, which is not big enough, so we need to look at the normal piece of this. So normal was stated that we could assume that in the problem, so we definitely have that. We can circle it and put stated. When I look at the NPP, it's pretty good, but it's definitely pushing the boundary of what I would be happy with in terms of the bumpiness here for such a small sample size. But we have it stated in the problem, and so that's fair to use. And then sample standard deviation S is going to be 3.13. And then for the old line, the random sample was stated again, and normal was stated as well. This NPP looks a lot better. I would use that without reservation. And then our sample standard deviation is S is equal to 4.76. So since we have two distinct groups or two independent groups, this is going to be a two-sample t-test. And then to get our test statistic and p-value, we're going to switch over to Excel. So give me a second and I'll see you over there. All right, so this is the Chapter 21 data sets, and we're going to start by using the method of the data analysis package to get our test statistic and p-value, and then I'll show you the other way next. So we do need to switch to the data ribbon, and then we're going to click on that data analysis. And up until now, we've always used that regression option. And now we're going to scroll down to the bottom of the list, and what we're looking for is the t-test, a two-sample with unequal variances. So that unequal variances means that we have different standard deviations. And I'll say, okay. And then I'm going to highlight my first column of data, the new line. And then I'll highlight the second column, the old line. And that's all we need. We'll say, okay. And then we get this output that shows up on a new page. So we expand this up so we can look at it. So the two numbers you want to pay attention to here are the test statistic. So that's 2.44. And then for the p-value, the alternative hypothesis was not equal to, and that's a two-tail alternative. So we'll look for the p-value for the two-tail. So I get 0.027 or so if I round. And so there we have everything we need to go back and finish up our conclusion. So this is one way that you can get that test statistic and p-value. And then let me show you the other way using that spreadsheet that I set up. Okay, so this is the spreadsheet that we've been using throughout this unit. And so if you want to continue using that's totally fine. I have it all set up for you. You're looking for the two sample t-test tab. And once you find that, you'll see you have two columns here to fill in. So we'll put the new line in this first one, 82.4 is our sample. 82.4 is our sample mean. 3.134 for the standard deviation and a sample size of 10. And then for the old line, we have a mean of 78, standard deviation of 4.761, and a sample size of 10. So you'll notice we have the same test statistic here, 2.44. And then our p-value is going to be the two-tail one. And I want to take a closer look at this. So when we did this with the data analysis package, we got 0.027. And this says 0.037. So what's going on? Because those are two different numbers, although they are very close. So it turns out that the formula for the degrees of freedom on a two-sample test is not as easy as the one on a one sample. You can't just subtract one. So it's a little more time consuming. It's not a hard formula, it just takes time to work it all out. And so the data analysis package uses that more complex formula for the degrees of freedom. There's an alternate acceptable way of figuring out those degrees of freedom, and that's to find the degrees of freedom for each sample individually or each group individually, and then choosing the smaller degrees of freedom between the two. And so for that reason, you're going to get a little bit different variation because that degrees of freedom controls how much probability is in the tails or not. So I'm happy with either p-value. If you gave me 0.027 or 0.037, I would be absolutely happy with either of those. All right, let's switch back to the PowerPoint so we can finish up the problem. All right, so I brought over our test statistic from Excel, the 2.44, and I brought over both of our p-values, the 0.027 and the 0.037. Either is fine. Our significance level, or alpha here, is 5%. Both of those are under the 5% cutoff, so we do reject the null hypothesis. So our conclusion here is, with a p-value of 0.027 or the 0.037, at the 5% significance level, we do have sufficient evidence to conclude that the mean beer production from the new line differs from the mean production on the old line. All right, so I want to take a look at these two distributions quick in terms of their box plots. So here we go. So that new line, you'll see that the box plot is much more condensed or compressed, meaning that those values are more consistent, and the old line is much more spread out. Okay, so bigger standard deviation. And then if we remember that X is representing the mean, and there is a visible difference there between those. So it's not surprising that the hypothesis test rejected the null hypothesis, because it does, at least to the eye, look like there's a difference